All right, well, today we're going to talk about buffers. So you should have your note sheet from class on buffers if you were here Friday. Otherwise, I will put a copy here on Canvas. So here we go with buffers. Hopefully you already read the beginning of the chapter on buffers like I asked you to. And I'm going to go through these notes. So here, buffers are solutions that resist a change in pH upon addition of small amounts of acid or base. So buffers are usually composed of a weak acid and its conjugate base in the form of a salt, or a weak base and its conjugate acid in the form of a salt. Buffers are extremely important to us as living creatures. We have buffers in our blood, for instance, that otherwise we couldn't maintain a constant pH with our blood, and we could actually die without that if the pH of your blood changes too much. Also, if you are trying to grow some type of bacteria or yeast in a lab, you always have to include a buffer in your agar so that as the yeast or bacteria is growing and metabolizing the waste products that are given off, and then the buffer will keep constant pH, or again, if something gets too acidic or too basic, living things will die. So the example here, this is a weak acid, acetic acid, and it is going to be with its conjugate base, which is sodium acetate in the form of a salt, because again, just the conjugate base by itself, C2H3O2 minus, doesn't exist by itself, so it has to be in a salt. So it's sodium acetate or potassium acetate or something like that. So acetic acid with sodium acetate can be a buffer, or ammonia and its conjugate acid. So ammonia is a weak base, its conjugate acid is NH4 plus. So in the form of a salt, it would be ammonium chloride, not HCl and NaOH or HCl and NaCl. Those are not weak acids with their conjugate base or weak bases with their conjugate acid. Okay, so tell whether the following pairs of substances would be a buffer. So would KCl and HCl be a buffer? No. HCl is a strong acid. With this HC3H5O3, and you can see that the conjugate part of it is here with this. So this is a salt. So this is a weak acid and its conjugate base in the form of a salt. So yes, this is a buffer. How about this one? C3H3. Okay, so this is, if we look carefully, this is a weak base. We talked about weak bases. This is an amine. If you were naming it, you name it. It's methylamine. And then over here, we can see here is that, plus it has picked up an H. So that part is CH3, NH3 plus. So that is the conjugate acid of this weak base. So yes, this is a buffer. Okay, and D, NaCl and NaOH. No, NaOH is a strong base. That's not a buffer. And here we have NaHCO3 and Na2CO3. So this is a weak acid. And this is its conjugate base. And so, yeah, this is a buffer. Okay, so looking at the weak acid with its conjugate base in water, you can see here's our weak acid in water. It makes H3O plus and its conjugate base. Okay, and so just like before, water is a pure liquid, so it doesn't go into the Ka expression. So the Ka expression being products over reactants, we would get H3O plus times x minus over hx, which is the products over reactants, equaling the Ka. So just rearranging that to put the H3O plus by itself, we would get H3O plus equals Ka times Hx, the weak acid, over its conjugate base. So this is the weak acid, this is its conjugate base. So what we're saying then is that if we add a small amount of OH minus or H plus, the ratio of those two shouldn't change too much. And that's how buffers work. So the ratio of the weak acid to weak base won't change very much when we add small amounts of acid or base. So this should be relatively a constant amount of H3O plus, which means the pH won't change much. But if you add a lot of acid or base to this, then it won't work. So buffers can only take small amounts of acid or base added to keep a constant pH. We can think of the common ion effect with Le Chatelier's principle. We talked about when you add a reactant, it pushes the reaction temporarily to make more products to get back to equilibrium. If you remove a product, it will pull it towards the products, or if you add a product, it will push it towards the reactants. That's Le Chatelier's principle by changing concentration. So when we add sodium acetate to acetic acid with a common ion effect, we can see we're adding more of this which is a product. So that's going to shift the equilibrium back that way. So that means that the dissociation of acetic acid then decreases when we add more of its conjugate base. Okay, so when we add its conjugate base, it causes the dissociation of the weak acid to be less than it normally would be. And the adding the strong acid or strong base to buffers, we're assuming that that small amount is going to be completely consumed by the reaction with the buffer. And then when we do those, we can do a calculation. We can calculate the new concentration of acid and base. And as long as they haven't changed too much, again, that H3O plus won't change much and the pH won't change much. Buffer capacity is the amount of acid or base that the buffer can neutralize before the pH begins to change to an appreciable degree. And the greater the amount of the conjugate acid-base pair, the more resistant to pH it is, to changing the pH. Okay, so the more resistant to pH changing, the greater the original amount of conjugate acid, conjugate base. Okay, so the higher the molarity of the acid to base, the higher the buffer capacity. So in the example, which has a higher buffer capacity? A buffer composed of 0.1 molar acetic acid and 0.1 molar sodium acetate, or a buffer composed of 1 molar acetic acid and 1 molar. Well, it would be this one, because the higher the concentration, the greater the buffer capacity. So that means starting with the 1 molar of each, it could adjust to a change in adding a little bit of acid and base to it better than when it's only 0.1 molar. It won't be able to handle that with as much as well. This Henderson-Hasselbalch equation is a shortcut for doing calculating pH of buffers. You can only use it with buffers. You can only use it when you have both you can only use when you have both the weak acid and conjugate base. If you only have one or the other, you can't use this. Okay, so this is only with buffers. You could have a weak base and its conjugate acid too. Otherwise, it's a shortcut. Instead of having to do an ice problem every time, you can just plug in the initial or the starting amount of base and acid. Again, we're assuming that you're only adding a little bit of, that there's only going to be a little dissociation of the weak acid to its base or from the weak base to its acid. Just like when we do our ice problems and we ignore X, we're assuming that the amount of ionization will be negligible. So it's just like ignoring X in our ice problems. Our ice problems. And this is for weak acids and weak bases. Sorry, our ice problems. Okay, so when Ka is small, or Kb. So for weak acids or weak bases. Okay, so for example, with this one, calculate the pH of a buffer composed of 0.5 molar acetic acid and 0.5 molar sodium acetate. The Ka of acetic acid is 1.8 times 10 to the minus fifth. So first of all, this is our equation, that the pH of the buffer will equal the pKa plus the log of the concentration of the base over the acid. So P before anything means minus the log of. So pKa means minus the log of the Ka. So in this case, the Ka is 1.8 times 10 to the minus fifth. So the log of 1.8 times 10 to the minus fifth is 4.74. Okay, so the pKa is 4.74. We plug that in, 4.74, point there. And then we plug in the concentration of the base. The base is this one. This is the base. And it's 0.5 molar. And the concentration of the acid, this is the acid, it's also 0.5 molar. So that'll be the log of 1, which is 0. So in this case, the pH equals 4.74. Okay, because that term just cancels out. Okay, so for that buffer, when you have equal concentrations of the base and the acid, the pH will equal the pKa. Let's look at the second problem. Calculate the pH of a buffer that's composed of 0.25 molar hydrofluoric acid and 0.2 molar sodium fluoride. The Ka is 6.8 times 10 to the minus fourth. So now the pKa equals minus the log of 6.8 times 10 to the minus 4. So the pKa is minus fourth is 3.17. So plugging that in, pH equals 3.17 plus the log of, now this is the base, and that's 0.2, and the acid is 0.25. So the log of 0.2 divided by 0.25 is negative 0.097. So 3.17 plus negative 0.097. So that pH equals 3.07. Okay, so Henderson-Hasselbalch, again, this equation is a shortcut. If we would have done it as an ice problem, we would have written out starting amounts of our acid and base. So in the first one, when we had acetic acid, CH3COOH plus water goes to CH3COO minus plus H3O plus. In this case, initially, we would have had 0.5 molar of this. Water doesn't have a concentration. 0.5 molar of this and 0 of this. This would have been minus X. This would have been plus X. This would have been plus X. This would have been 0.5 minus X, 0.5 plus X, and X. So in our Ka expression, we would have had 0.5 plus X times X over 0.5 minus X. And the Ka is 1.8 times 10 to the minus fifth. So then this is where we can say, oh, well, the Ka is small, so we can ignore this X and this X, which means we would just have 0.5 X over 0.5 equals 1.8 times 10 to the minus fifth. We can cancel off those 0.5s and we would end up with X equals 1.8 times 10 to the minus fifth. X is the H3O plus. So when we take minus the log of 1.8 times 10 to the minus fifth, we'll get 4.74. Okay, so the Henderson-Hasselbalch equation is just exactly like doing an ice problem with the shortcut. We're saying we can ignore this and this so that we're just plugging in the initial concentrations of those two into the Ka expression. And it's exactly the same difference. Okay, so again, though, you can only use this when you have a buffer. And of course, I will end with a joke. Why did the weak acid go to the gym? To become buffer.